So, hello guys, it's me, Franz Kingstein, and today I'm here with another tutorial series, a tutorial video. So today we're going to see about encoder-decoder model. So this is a base for generative model and of course a language translation model and whatnot. It is not a main thing which use in many fields like chat generation, even image generation too sometimes uses this because it used to convert text to image and etc. Like so sometimes it has been used in many fields, so it's very important for us to see this. So before getting into the coding part, so let us learn some theory concepts based on this. So let's get into it. And here we go again with this right theory. And first, let us see what is an encoder-decoder model is. So, as we see, if you give an input text, the encoder model will just convert it into a vector, and the vector is being read by a decoder model. It's a separate model, and we just get in a summary. So, I know it's a bit confusing, so let me tell it from scratch, and I try to make my level best to make myself clear. So the input text is the text what we give or what a user, what a human language is. So as we know that our computers will find it difficult to process or to analyze text. So it is important for us to convert each and every text, each and every word into a particular vector or numbers equals in such a way that it makes the computer easy to understand. So in order to do this, we use this encoder-decoder model and no, we use encoder model here. So we take the input and in this encoder model, each word is being converted into vector. So what is a vector? As we study in our school times, we use x-axis, y-axis and z-axis in graph, right? The exact same, but on the exact same concept is applied here, like giving a coordinates for each and every word. But instead of using a three-dimensional space, we're using a multi-dimensional space in such a way that as the dimensions get higher, the accuracy of the model would be higher. So this is how an encoder model works. So encoder is being taught to be work. So we have a set of vectors, vector library, vector content over here, and we use this vector content to get the output. How using a decoder model. So decoder again I get a user input. It's not been mentioned here, but again gets a user input mapped with a particular vector over here and gives a particular output based on user input as well as the context vector. So this is how basically a encoder-decoder model works. So how, in what way the model encodes and what way the model decodes? Now we can see a particular thing called one-hot encoding, which is widely used, but instead of this only we're going for a vector representation. But before vector representation, this was the one that's followed. So, and as you can see, for three colors over here, and each and every word we marked a particular column. For example, red means we just marked a thing as red, and with the other colors have been marked as 0. And even if yellow, the red and the green thing have been marked as 0 and only the yellow has been marked as 1. So this is how a one-hot encoding works. So this is the thing which was being used before the vector representation was created. But now this is how the vector represent looks. But the result, okay, before getting into the vector representation, why are we using a vector representation instead of a one-hot encoding in the sense? For three words, we can use three cross except three cross anything as a table. But what if we have a million words? What if we have a lot of words where the table or a structured data would not be a perfect suit? So that's where vector embedding or vector representation comes into place. So let me zoom it for a clearer understanding. So you can, you can see, this is a three-dimensional representation of data where the things like wolf, dog, cat, kitten, and of course over that say we have apple and banana. Instead of representing as a table, it is representing as a vector or a three-dimensional space or n-dimensional space. So this could save a lot of storage, maybe more than efficient than one-hot encoding. So because it also uses for us to find similarity between similarity between 2 points by finding the distance between them or finding the similarity index between them. So this is how vector embedding is widely used in this field. So let me also show. So this is how LSTM work. Where did LSTM come in? So as you know, we know this black box as encoder and decoder. But what is this inside encoder and decoder model? It is the LSTM model. So but still people like I could hear like what is LSTM? It is a neural network model where it is a hybrid model, or it is a next generation of recurrent neural network. So what is a recurrent neural network means? It is a neural network as how a brain functions like neural network. So the same concept is being used here, but the thing is that the regular neural network doesn't have any memory, but this LSTM does have two types of memory, that is a short-term memory as well as a long-term memory. So H here represented as a long-term memory where the information from the previous data has been stored, but the short-term memory is C. It is also a previous memory, but yet only a small number of data has been stored in a C, and a long size of data or a big amount of data has been stored in this H parameter. So we had a function f of t, and we just combine the previous the historical or the previous data with the current data C. Current previous data x of t is the input here, and historical data h of t is been also been added to get the current data cft. So this is the theory concept. So let's dive into the coding part. Okay, let's go. So here. So here is how the coding goes. So our steps would be first importing a library models as we do regularly in Python, and of course we should define the model parameters like what we should do, what the model should be, what is the size of the model, etc. And we should define two encoding model as well as a decoding model, and we need to define the model by combining it too. So let us start coding it, and I hope the screen is visible. So yeah, so we are using TensorFlow library. So as people know and also don't know, okay, fine. I just use it as TensorFlow. Oh, no, TensorFlow, fine, better. So TensorFlow is a library that could. I just make myself clear. Okay, fine. Sorry for confusion. So TensorFlow is being stated both as a library as well as a framework. We call it library because it has pre-written codes in it so that they could import it and can be used. Then also called as a framework because it has the setups environment for us to perform things, as well as it has high-level API connections, so high-level things like Keras, etc. So the choice is yours. I can just call it as a library, or you can call it as a framework. So let us get into coding without any further delay. So from TensorFlow dot Keras yet another thing, and layers that contains the particular things for deep learning and neural networks. And import you should have input layer input layer, a dense layer, as well as the maintain LSTM. Yeah, great. And let us also from TensorFlow dot Keras, let us import model. So this is where we combine the encoder and decoder model using this model. So we actually can use NumPy. So NumPy is a library which is widely being used in a number like in math calculations, and of course sometimes some statistical and probability formulas and some advanced formulas or concepts have been mathematical concepts could be implemented here in NumPy. So let's run the first cell. I hope things go on smoothly. Okay, great. So let us now define the model parameters. We have only one model parameter called as latent. So let's go with the model parameters, that is latent is equal to, I'm using I can use 128. For anything anyways, you can also use 256 256 or 512, but I am using 256 because it could be a medium number so that my system could manage this. So this is the thing we can use. This is the only parameter. This is essential for encoder decoder model. So as the A suggests, you can also use stamps etc. But it's enough for us for now. Only for learning purpose, you could use latent dimension. So let us now create encoder model. So my encoder model starts with the encoder input, which is equal to my input model as we imported, right? So that has a shape, that has a shape of none and 100. And I guess that's missing now. Okay. So, and we also have encoder as a such LSTM model. So that is LSTM model, and it has a latent dimension, as we mentioned. Condatly could have been mentioned as not latent them, and we should definitely return the state is equal to true. Yeah, that's better. And of course we should also create an output, and we also create a hidden state, that is state heads, that I was just calling as a history, but it's in hidden. And of course current state, that is C, that is equal to encoder, that is we created a LSC model, right? So with encoder input, so this is combined encoder input as well as we are just using encoder LSTM with input of encoder input to create an encoder output. So nothing complicated. We're creating an inverter output, the state H, that is hidden state, as well as the current state, using LSTM with the input. That's it. Very simple. I hope I made myself clear. And of course, we need to store the states, right? Encoder states, state is for better understanding, and we can just store it as a list state C. Yes, so now let us run this with this error. Oh wow, latent dim is not been defined because we didn't run this. Right? I hope. Okay, so resistant GPU devices, my GPU is not been connected. So now the same concept we used above should be used below, because encoder decoder model has the same architecture. The only difference is the input and the output. So let us create a decoder input is equal to, let us use an input, a layer of shape, am I correct? Yeah, shape is equal to none, nothing. and 100 as encoder model does. So let us also create a decoder LSTM that is equal to a LSTM method that is latent dimensional, yeah, and my return sequence should be true, yeah, and of course the initial state. This is different from the previous one because we just created the encoder state that could be used here in this decoder model. So that can also we had a decoder output. As you can guess, output is equal to decoder of LSTM, which has a parameter of decoder input. Yep, and of course, and also let us also create a dense model. Then decoder dense model to finally process the hidden layer to process that 100, and we have activation equal to softmax. The softmax is an activation layer which could be used when the output is multiple or many. So in upcoming videos I will explain what is softmax and how it could be used. So let us also create another decoder output. That is the final output is equal to decoder of tens. That is decoder output the previous one. Yeah, so okay, that's correct. So I hope it runs and we have value error here. So what is the value error? Keyword. Oh. It's a latent time, written sequence is true. And we have a thing called initial state as encoder state is correct, right? State. Okay. 56. Well, so let me check it. Where just wait a minute. I guess so. Size. So let us try running this. So I can see the cap. Yeah, that's better. So we just decoder data like we shouldn't use input sequence and decoder out softmax. I just use a capital S, and of course let us define a model right now. That is model is equal to models. So we have input as encoder. Not input, encoder input and decoder inputs, and so my output should be in such a way that there should be a decoder output, yes, as it says. So I didn't mention it as yes. Okay, and yeah, let's go. And of course let us compile the model right now. So compile optimizer is equal to Adam optimizer, and it considers only and of course loss is equal to categorical cross entropy. Let us cross entropy, and that's it. If it runs, I could just start explaining data per like what is the atom and what is less cross entropy. So let me first check it, then explain you what is this. So yeah, the code's running, and so yeah, and this code's run. So before getting the summary, That is the moral summary. And before ending the video, so let me explain what is atom and categorical cross entropy. So atom is an optimization function where we learn backtracking, right? So in backtracking, atom combines two things, that is momentum and RM plus prop. That is root mean square error. And the momentum is it is how the previous training, right? The difference between the so there's a difference between the actual output and the predicted output when we calculate, and it could penalize more in order to get a good accuracy. It also the RMS fraud is root mean square. That's the same thing, but it squares the it squares the difference between the input and the output in order to get in order to get a good accuracy. So this categorical cross entropy, it is a loss function, for multiple different category, this make okay this not okay. So let me explain atom and categorical cross entropy. So atom, it is a optimizer function that is in while backtracking. We consider the difference between the actual value minus the unpredicted value. So this difference we use in order to backtrack. So in order to penalize more, in order to get a good accuracy, this atom considers the thing, that is momentum and the RMS from. So RMS from first, it is a root mean square error. It's the difference between the real value and the weighted value. It squares it and gives penalty according to it. This momentum, it is how the learning curve is. That is how well the model learns in the previous data or in the previous iteration. So this two is being combined in order to get a good accuracy. Atom has been used. So categorical cross entropy, it is a loss function. I mean, not exactly uh, related to a difference or different related to loss, but it is like a one-hot encoding where it just puts one where the output is correctly being mapped and remaining things will be zero. Like we see one-hot encoding, right, where we see red color has been marked as 1 if the text has been red, and the other two things have been marked as 0. It is not been mentioned. The similar thing will be done here. Here we use that concept in order to okay, fine. In order to get the output, in order to put it in the output. So that's it for today. In the next part, we can try using a real data set where we can use English to French data set in order to make prediction with this encoder-decoder model. So thank you all, guys. See you, and sorry for all the mistakes and the stumbles which I have done.